Now that we have wrapped up discussing the analytic improvement cycle, let's discuss a little more deeply how time, terrain, and behavior can be used to improve our analytics and their output. In this lesson, we provide an overview of some approaches to visualize the time, terrain, and behavior dimensions as they apply to our analytic results. Starting with the time dimension, one of the first things we're going to notice is the frequency of hits or results returned from our analytic. We may also notice uneven volume of hits over time. For example, spikes in events during certain days of the week or certain times of day. For terrain, one thing to make sure of is that we're getting results back from all the hosts we anticipate are there, and identify any unexpected gaps that we need to explain. Perhaps hosts are down, or sensors are broken, or data is coming in from those hosts in a way we didn't expect. Conversely, we can look for unusually high volume from a certain host, or subnets, which could indicate a different baseline behavior for that segment of the network. As for behavior, do we get back all the events we expected? If we are using threat emulation, we can use those events to answer this question. We also want to consider, do the results of our analytics conform with the intent of the analytic? So, does the analytic output tell us enough information to answer the question we need answered? For example, if we are writing an analytic that is supposed to identify the use of remote desktop sessions for lateral movement, does our analytic output that information in a way that is useful to us? Although there are three primary dimensions to consider in threat hunting, three-dimensional visualizations are often too confusing to read and interpret. So, we often project those three dimensions onto the two-dimensional visualizations you tend to see when you're looking at dashboards in many SIEMs. In this lesson, we'll cover one type of two-dimensional representation of this three-dimensional space called a heat map. We'll also look briefly at the classic timeline view. In Module 6, we'll show a graph visualization of typical activity in a network of systems and how it can be filtered down to focus on the malicious nodes using combinations of analytics we're developing through this methodology. For now, let's focus on a few variations of the heat map visualization, which plots two dimensions on the x and y axes and represents a third dimension as a color. When we create a heat map, we will assign the x and y axes to two dimensions of threat hunting. We will then map the number of events that occur at each of the intersections of those two axes. In this simple example, we're demonstrating a heat map that shows counts of results returned from our analytic mapped against machines, which is our unit of terrain in this case, and days, which is our unit of time. Looking at this map, we can see that machine X5057 on December 12th, there were no events returned by the analytic. However, box X3415 had 10 events on December 16th that matched the analytic that we wrote. And so, looking at this heat map, several anomalies emerge. On machine X8401, there was a sudden spike of activity on December 14th, and there was no activity before or after. On machine X1423, there was noticeably more activity on days 4 and 5, and there seems to be an elevated level of activity on day 4. The focus is on machines X1423 and X3415, starting after December 15th. So, what we might infer from this heat map is perhaps there's an initial compromise on box X8401 on December 14th. The adversary then moved across other hosts on December 15th, or perhaps there's some background activity that also occurred on that day. And then the adversary focused on X1423 and X3415 on the 16th and 17th. If we had only seen these results in a table, this pattern may not have emerged to us. However, with this visualization, we can quickly see those patterns. Let's rotate our three-dimensional cube of cyber hunting space to show a different cross-section, this time of time and behavior. This will show us how often, for example, on how many hosts each behavior occurs on each day. This can provide us indications of a sudden increase in activity of different behaviors day by day. In this example, we can see that lateral movement using SMB only occurred on December 14th, and also that across the behaviors on our heat map, almost all were executed on December 16th. Remote services and accessibility features techniques were used primarily on December 15th, with a couple more instances used in subsequent days. We could use this kind of knowledge to gauge where adversaries are in their intrusion lifecycle, so we might expect to see something like more lateral movement, followed by discovery, followed by privilege escalation, followed by exploration techniques. So, following that logic, we could perhaps assume, based on the data presented in the heat map, that the adversary successfully moved laterally to all of their desired targets on the 14th, and subsequent activity was then performed. We can also rotate the cube to get a cross-section of terrain and behavior. This shows us how often behaviors occur across different hosts. We can also modify the heat maps to show on how many days a given behavior occurred on a given host. This can help us see regular patterns of activity, sudden spikes in activity, or unique events. As we can see in this heat map, the accessibility features technique occurs across all hosts, although infrequently. Conversely, the credential dumping technique only occurs on one host at one time. We might be able to infer from this that this host might be the only one initially infected before the adversary moved laterally, using credentials found on that host. Now that we have discussed several different ways of creating heat maps using the time, terrain, and behavior dimensions, let's review when heat maps in general can be useful and what their limitations are. Generally, heat maps shine when there is some level of anticipated background noise. If our analytic is very precise and there are no false positives, we may be better off with just a standard alert. We also need to consider the level of the anticipated noise versus the anticipated number of events when malicious activities occur. If the numbers are too similar, the malicious events will not stand out. So for example, if we have 100 events normally, and when it's used maliciously, we will just see one more event, we're unlikely to notice that variation in the heat map. In cases where one behavior alone may not stand out, you might want to consider amalgamating several detections together as indicators of higher risk. Heat maps are of limited use in low and slow campaigns as well. Since the variation of events tends to be very low, it'll be very hard to derive information out of a heat map indicating such a campaign is going on. When thinking about how to set the bins for the different dimensions, we should try to do so in a way that would be comparable to the scale of anticipated attack. Unfortunately, there is no universal answer to what the bin count should be. We will have to work with them as we iterate through our analytic so that we can get a heat map that shows malicious activities standing out from the benign background noise. A good generic starting point might be, when mapping time by terrain, for example, is to bin time by day and terrain by individual machines. So you might start with a week's worth of time, as we did in our heat map examples, and a map of all the hosts or a subset of the hosts into that heat map. If you have a very large environment, mapping all the endpoints might not be practical, and you may need to consider breaking the maps up into sections based on subnet or some other categorization scheme, or using a filtering threshold before you move to the heat map visualization. As we mentioned before, we need to be careful that we don't make the bins too small, or else it will look like static, as values will tend toward only the extremes, for example, just a 0 or a 1 in every bin. If, on the other hand, the bins are too big, it will just all blend together and no values will stand out as unusual from the others. So that's enough of the heat map theory. Let's look at a practical application of it. Here we have a heat map we generated as part of a cyber exercise on a live production network. In this case, our analytic is aggregating the occurrence of suspicious commands together and then mapping that across terrain and time. As we can see, there's a fair amount of background activity going on across many hosts. However, we do initially see two unusual patterns. The first is that computer 17 has abnormally high number of events compared to all of the other hosts, and that happens on multiple days. Second, on day 14, we see a higher number of events across many different hosts. We don't necessarily know if these are bad, but it does provide us with an initial focus point to start investigating. The first thing we might do is look at host number 17 and check out what's going on there. In this case, we found out that host 17 was a software developer's machine, and they were doing a lot of activity that was being treated by our analytic as suspicious. So we removed that computer from the data set and filtered it out for the second iteration of the heat map. Now that we've excluded the activity from computer 17 based on our first investigation, some new elements appear to us as standouts in this heat map. We still see the large amount of suspicious activity on day 14 across many hosts, but we also now see that computer 16 and computer 30 stand out more for the amount of activity they have across multiple days. Computer 16 alone has more than 3 times as many events as any other computer for a given day. As the next step in our investigation, we decide to triage the events on computer 16 and 30. We find out that this was indeed true positive malicious activity. And so through just 2 iterations of our heat map, we have successfully identified malicious activity out of all of the background noise. Here is the same heat map, but tagged with what the blue team would have found through the heat map versus what was missed. As we can see, the heat map helped us largely find the malicious activity on the 14th and identify computers 16 and 30. We did miss some activity from machines elsewhere in the network, but this gave us a good starting point for our investigation. Now think about if all of this same data had been displayed in a typical table. It's very likely we would have missed many of these patterns, and it would have taken us probably longer to find the things that we wanted to investigate first. This is a good example of how a heat map can help us, and part of why it works is due to the nature of the analytic that's being used for it. The quick series of suspicious commands is the analytic, which we have published in CAR, and by its nature, it works because when an adversary is on a machine, they often execute many suspicious commands that normally we would have a lower level of background activity. And that's the sweet spot use case for a heat map. So enough about heat maps. Let's look at another common visualization we see in modern SIEMs, the timeline. Often this is used as a visualization of the count of events returned by the analytic across all terrain binned by time, with time being adjusted often by the amount of time over which data is collected for the search. A timeline is just a further flattening of the 3-dimensional time, terrain, and behavior cube. So a timeline is a related projection of a time by behavior heat map. Each of these visualizations can be thought of as a different way to project the 3-dimensional space onto the 2-dimensional screen, and each has pros and cons. In this lesson, we showed some examples of how to visualize the 3 cyber hunting dimensions onto a 2-dimensional screen. Specifically, we dove into how and when to use a heat map visualization.